In this video, I'm going to introduce to you how we can design a load circuit for maximum power transfer or perhaps maximum voltage or maximum current. Because that's something we often want to do when we have a load. We want to maximize either some information signal or the power transfer to that load circuit. So we might be given an active circuit and a passive circuit that are connected. What is an active circuit? Well, that is a circuit that has at least one independent source. And a passive circuit will not have any independent sources. It won't have any amplifiers or anything like that. So it just has passive elements. Passive elements could include resistors, capacitors, and inductors. So we would generally think of an active circuit as a power supply and then the passive circuit as a load. And we learned recently that you can reduce the active circuit down to an equivalent circuit. So here I've drawn the Thevenin equivalent circuit as the equivalent for the power supply. And then we've reduced the load down to a single resistor. Of course, if you have L's and C's, you probably won't want to use just resistance, but we'll focus on the purely resistive case here because this is an introduction to this concept. So let's think about the voltage that appears across this load and the current that flows through it. Using voltage divider, we can write this. So given the power supply, we often think of the Thevenin equivalent resistance as fixed, but the load is what we could design. Similarly, we can write an equation for the current simply using Ohm's law. Now we can see that if we want to maximize the load voltage, we make the load resistor much bigger than the Thevenin resistance. And you could see in that case then that VL is going to approach V Thevenin. If we want to maximize the current, then we have to let the load resistance be much smaller than the Thevenin resistance. If we want to maximize the power transferred, it's a little bit more complex, but it's not too bad. First, we'll write power in the load as IV. Using those expressions up above, we can write it like this. Now we take the derivative of the power with respect to RL, and we then set that to equal to 0 to find the extremum. Setting that to 0 to solve for the extremum, we then have this. Okay, now we can do this. Basically, we can divide both sides by V Thevenin squared, and then we just focus on this part in parentheses here. And we'll move the negative term to the other side of the equation. We can cancel that. So now we have this. And that will lead us to the following. So that's our condition for maximum power transfer. Also, we can use that condition then and plug it back into our power expression. There's our power expression. And we can calculate what the maximum power transferred is. So we'll use this R Thevenin equals RL, and we'll write our maximum power as this. Right, so that just comes from the equation above, and everywhere we see a load, well, we know its value for maximum power transfer, which is just R Thevenin. We put that in, and you get this expression. You could see problems where you have a circuit and you're asked to design a load for maximum power transfer. So what you want to do there is reduce the active part of the circuit down to its Thevenin equivalent, and then you can easily find the load that you need to maximize power transfer. You could find the maximum power transferred itself using this equation. And then if you wanted to maximize current or voltage, well, these are the various equations that you'll use for that. Okay, so that is one reason we are interested in Thevenin analysis, is that we can simplify a power source down to just a single voltage source and a single resistor, and then we can learn things about the kind of load that we want. Remember to like the video and subscribe to the channel. Thanks and have a good day.